Okay, so last time we talked about memory, and the program is located in microcontrollers in read-only memory. In Windows computers, the program is located in hard drive, and when you open the program, it is actually copied from hard drive to random access memory because it's a Neumann architecture. But generally, you can still like imagine that the program is located in some memory, and basically you give the address and it gives you an instruction, one instruction of the program. And in microcontrollers, it's like physically in different locations. And in microcontrollers, the memory is almost always built as flash memory, flash technology. It's just called flash always, often for simplicity. So we have flash memory in which the program is located. And the program consists of instructions and, addition, subtraction, and so on. It's just written there what to do. So our simple microcontroller, as we have decided, will have instructions. Each instruction will be 16 bits long. And as you can see, I changed this memory to 16 bits. And so each instruction is 16 bits. And for example, I can manually type in some instruction value. So I don't know, I'll write here 1, 2, 3, 4. The next memory location will be, for example, instruction that is something like 5555 or whatever. Here is 6969. Here is A, B, C, D, and so on. So when you write a code in C programming language and you press compile, then these machine language instructions are just generated. Compiler translates everything into assembly language, optimizer optimizes the code, and then the assembly language is translated into machine code, into these ones and zeros, which physically, with their high and low level of each bit, switch and control the rest of the microcontroller. And we can flash microcontrollers with special programming tool, and then these instructions just remain in flash memory. So, but how do we read the values and so on? The reading of program is done using register, which is called program counter, PC. PC. It's short for program counter. And program counter is the pointer which points to the next instruction that will be read from our flash memory. I don't know, I'll maybe put a text here, flash memory, program memory. So this is our flash memory or program memory. I will locate it like this. So this flash memory has input address, and we will just directly connect the address control input to program counter. And as you can see, program counter says 0, and this flash memory selects the data that is located in memory location number 0. And since we have 16-bit wide memory, address 0 contains 1, 2, 3, 4, a 16-bit number. These are numbers in hexadecimal format. And I can put, for example, an output here, set its data bits to 16, for example, connect them here, and you can see that this line says, some number, which is 1, 2, 3, 4. So program counter, this special register program counter, is the thing that controls which instruction will be performed next. Okay, so it's like a pointer to flash memory, and it has an input called clear when one pin value set to 0 asynchronously. So I will put a button, and this is the reset button. The reset button, it is located, for example, in West. And so the idea is the following. When you press button reset, what it does when you press button reset on your computer or on microcontroller, what it does is it just sets program counter to 0, and program automatically jumps to the beginning to address 00. And practically all microcontrollers start at program at address 00. There is one small exception. There is this company Texas Instruments, which creates microcontrollers in series MSP 430, and they start the program at the end of flash memory. Their reset vector is located at the end of flash memory, address to all ones, 111, 111, 111, 111. But that's the only exception that I know. All other microcontrollers start their program at address 00. So resetting microcontroller simply means setting program counter to 0. Okay. And how does the microcontroller go through the instructions? It goes in the following way. Program counter shows the next instruction to perform, but every time we have a clock signal, which is located here, program counter is simply incremented by 1. Let's see, we have wiring, clock. This will be our clock signal. And, you know, on each clock, program counter is just incremented by 1. So basically, we will add here an adder. We can actually use our own adder here. So program counter is one input, and the other input is just constant number 1. Let's say 8 data bits, just 1. And it goes in here. And in this case, carry in is 0, so we don't really need it. But well, we have this input, so we have to put it, but carry in is just 0. And the result is the previous value of program counter plus 1. So program counter is 0, and on the next rising edge of clock, it is incremented to 1. And on so it says 1, and immediately this 8-bit adder adds 1, and the program counter input is set to 2. And since this is a latched register, its contents are only updated on rising edge of the clock. So, you know, it's not like starting to randomly count to some big number, but on each clock, it just increments by 1. It changes the address of the flash memory to the next address, and the next contents of that address are output and sent into the microcontroller. And this is how microcontroller performs the instructions. Clock goes ahead, and program counter simply increments on each clock and jumps to the next instruction. And the microcontroller receives instructions one by one on each clock. Microcontroller receives the next instruction. And when I press reset on my computer, program counter simply resets to 0, and the program returns to the beginning. Okay, so you can write in the chat if you understood this concept or not. Okay, if it's everything is clear and easy to understand. Okay, where is the chat? Okay, it's clear. Great. Okay, so and now there's a small modification to what I just did. There is this convention that, you know, values are read during the rising edge and written during the falling edge. So actually program counter's clock is inverted. It's a small technicality, you don't have to really worry about it, but the program counter is updated on the falling edge because during the rising edge, the data is read into the microcontroller. So actually what happens is on rising edge, nothing really happens, and program counter switches to the next instruction during the falling edge. You know, because on rising edge, microcontroller reads the value and starts to execute it. So program counter updates on falling edge. And also for branch instructions, it's going to be used that way also. But you know, that's just technicality. So, and program counter is the one that controls which instruction will be performed next. And now we will switch to a little bit more advanced microcontroller, which is what we completed last year, you know, just go through the functions. So basically this is like a full microcontroller CPU. And in microcontrollers, generally program is like separate part, random access memory is separate part, and central processing unit is a separate part. It's just that in microcontrollers, these are all located on single chip, but also in the chip there, like program memory is in one corner of the chip, RAM is in another, and CPU is in the middle. So in CPU, we have right here program counter, and you know, it's just incremented by 1 every time. And here we connect the random access memory address pointer, and here data comes in. Okay, one more thing, you know, just logical question. If program counter is 8-bit number, how many instructions can we write in our flash memory? 256, because, you know, after 255, program counter will overflow to 0. So obviously, you know, program counter size determines how many instructions, how big the program memory can be. So for example, in Atmel microcontrollers, it's 16-bit register, for example. You know, in some simple old 8-bit microcontrollers. So it's 16 bits. So it's 2 to the power of 16. So 2 to the power of 16 is, for example, 65 kilobytes would be the limit maximum size of flash memory for a microcontroller that has program counter that is 16 bits. For example, our Logisim microcontroller has 8-bit program counter, so we can only make programs that are up to 256 instructions long. That's all, you know. For example, ARM microcontrollers, right here, ARM microcontroller is a 32-bit microcontroller, so its program counter is actually located in one of the registers, and its size is 32 bits. So what is the maximum length of a flash memory in ARM microcontrollers? It is 2, sorry, 2 to the power of 32 is this much, divided by, oops, 2 to the power of 32 divided by 1024. This will be kilobytes, this will be megabytes, and this will be gigabytes. So if program counter is 32 bits long, maximum flash memory size in ARM microcontroller would be 4 gigabytes. And because ARM microcontrollers are von Neumann architecture, actually flash plus random access memory maximum size of ARM processors is 4 gigabytes. So this is kind of a thing to think about. The newest ARM processors that will be used in, for example, Apple computers, their program counter will be even wider. It's not going to be 32 bits. It's probably going to be 64-bit register. And there you have more memory than, I think, atoms in the space, maybe. But generally, program counter kind of limits how big the flash memory can be. And the ARM processors have it 32 bits, so it's 4 gigabyte maximum size. But if you need more than 4 gigabytes of flash, then probably you are already talking about a computer, desktop, or Linux computer. So you would not really be using a microcontroller. So 4 gigs for microcontrollers is really, really a lot, right? So, this is just the connection between program counter and flash memory. Okay, so our program counter is 8 bits, so flash memory address bit width is also 8 bits. But data, 16-bit data. Okay, so now let's move on to the microcontroller. And here's the program counter. And there is also another convention that when data comes in, it does not go directly to microcontroller, but it is first stored in instruction register, because some instructions modify program counter. For example, if, then, else constructions modify program counter. For example, if A equal to B, do one thing, and if not, do something else. Well, how can you do something else? By jumping with program counter to a different location in flash memory. So some instructions modify program counter, and to avoid a situation where program counter points to one instruction, then it's modified, and at the same time the instruction that we read, which modifies program counter, also is modified. We need to somehow fixate this thing. We need to organize it. So first of all, program counter is clocked. And also this instruction register is clocked, and they are clocked in opposite phases. So program counter modifies on falling edge, but instruction register updates on rising edge. As a result, if the instruction modifies program counter, then instruction is updated only on the next rising edge clock. So modifying program counter doesn't immediately change something at the data input. Okay, so we have this program counter. Program counter points to, for example, instruction number 0. Instruction number 0 contents come into the CPU. Instruction register stores or buffers it, and just saves it until the next rising edge of the clock. And this instruction is first sent into instruction decoder. Instruction decoder is a special logic unit in microcontroller which receives the instruction. It expands the instruction bits and sends the control signals on all of the microcontroller parts, depending on what instruction you need to do. And we will go through all of the instructions that microcontrollers can perform, and you will actually kind of quickly understand how this instruction decoder makes decisions. So what parts of the CPU do we have? We have arithmetic logic unit, for example. It has operation selection input, right? So instruction decoder receives the instruction and it needs to extract the operation select signal from the instruction. And in our simple microcontroller, it will actually be done in a simple way. For example, I have made this documentation of our Logicsim microcontroller, and for simplicity, it's organized in the following way. Top 4 bits are just operation code for arithmetic logic unit instructions, and it will be 0, 0, 0, 0. Next 4 bits select register A in general purpose register, which basically says in which register to store the result. Next 4 bits will be operation, and the last 4 bits will be register that would be used in arithmetic logic instructions. For example, if you want to add register 5, I'll write it here, register R5 equal R5 plus R7, that would just set first 4 bits 0, 0, 0, 0, next 4 bits would be register in which to store the result. So register R5, which basically will be just number 5. And number 5 in binary is 0, 1, 0, 1. Next 4 bits will be operation. For example, I said plus, well, let's change it to something more interesting. For example, and R7. So and instruction is instruction number 8. So in binary, it's 1, 0, 0, 0. And the last 4 bits are the second register, register 7. So 7 in binary is 0, 1, 1, 1. Okay, so this operation code will be written in the flash memory. I can actually go and type it in right now. So here's our microcontroller, MCU, program memory. Let's say that instruction at the beginning is 0, 0, 0, 0, which is 0, 0, 1, 0, 1 is 5, 1, 0, 0, 0 is 8, and finally 0, 1, 1, 1 is 7. So program memory, when you write a code and you compile the compiler, if you write, for example, A is equal A plus B, it will translate it to something like this. It will be stored in flash memory in some location. And okay, so let's reset. And when the instruction is read, this instruction decoder should split the instruction in such a way that, for example, these 4 bits go into register A, next 4 bits go into arithmetic logic unit operation selector, and the last 4 bits go into select B. Okay, because we decided that it would be a way to do it. And this is exactly what the instruction decoder does. Let's see, for example, yeah, this is the instruction. We will do 1 clock. So we will do the rising edge of the clock. During rising edge of the clock, this instruction register latches the instruction. So it reads instruction into itself and forwards to the processor so that, it's fixed until the next rising edge of the clock. So right now it's just fixed. And what instruction decoder does, if we go inside of it, actually, it's just, you know, cables and wirings. So we said that, for example, the next 4 bits, the second upmost 4 bits will be destination register. Well, that means that from the instruction, we use splitter and we extract bits number 8, 9, 10, 11, and we just forward them to address A of our general purpose register. And if I click on it, it says 5, because these 4 bits are number 5. So actually, instruction decoder simply forwards these 4 bits to general purpose register select A input, and it's 5, and general purpose register forwards the contents of register 5 to arithmetic logic unit. Okay, let's put some numbers in so there's some action. Let's say R5 is 69 and R7 is 96, okay, in hexadecimal numbers. So programmer, it will be binary 0, 1, 1, 0, 1, 0, 0, 1. I'll write it in Notepad. 0, 1, 1, 0, 1, 0, 0, 1. Oh no, this is a bad example. The result will be 0. Okay, instead of 96, we will have number 7 maybe. Okay, 77. What is hex for 77? We go to this calculator, we write 77, and it is 0, 1, 1, 1, 0, 1, 1, 1. Okay, so and operation, we wanted it to do and, I think. So let's check it out. What happens in our CPU? So this is 5. Then instruction decoder simply forwards the next 4 bits, 1, 0, 0, 0, to arithmetic logic unit operation selector, which is 8 in decimal. Then the last 4 bits, it simply forwards to general purpose register input number B. It says 7, so it selects register number 7 as B. It's so here contents is 105 and here is 119. If we convert these numbers into decimal, and and actually arithmetic logic unit already outputs the result. It says 97. Let's see, is it true? So and on these two numbers is 0 and 0 is 0, 1 and 1 is 1. Here is also 1, here is 0, 0, 0, 0, and 1. How much is it in decimal? So binary is 0, 1, 1, 0, 0, 0, 0, 1. Oops. Like this. Is it correct? Oh, no. Okay, yeah, it's in decimal 97. So this arithmetic logic unit calculated everything correctly, right? And since we selected register number 5 as the destination register, the signal goes in here 97 and it will be written into the register R5 on the falling edge of the clock. And during the falling edge of the clock, the value is written into the register, and also program counter is incremented by 1. But you see, program counter changed, but instruction register value did not change. That is why they work in the opposite phases. One second, please. I'll stop share. Okay, so yeah, as I said, program counter and instruction register work in opposite phases. So when we write, program counter changes, but the address did not change and did not mess up everything in this processor. The instruction will change only on the next rising edge. Okay, so this is why instruction register, this is buffered and is opposite of program counter change. Okay, so our instruction set these control signals, and the result should be written into register R5. It says 61, and if we check out in this calculator, in hexadecimal format, it's 61. The result is 61. Okay, so this processor kind of does everything as necessary. So instruction decoder just, forwards each of these signal lines to the appropriate location. And initially, if we're talking only about arithmetic and logic instructions, let's say in our case, bottom 3 bits are address B, middle 4 bits is operation selector, next 3 bits are address A, and top bits are used to control some control signals. For example, should we write to general purpose register or not? Should we increment program counter by 1 or by something else, and so on. So the top 4 bits will be used for control of other signals. And as you can see, there are many, many other signals. So we talked about select A, select B, select operation, but actually there will be more signals in a second. To understand the other control signals, we will just have to walk slowly through all the instructions that the processor can do, and it will get clear for you, I hope. So let's look at a microcontroller. For example, I will now just show you the documentation of a simple 8-bit microcontroller, Atmel AVR microcontroller, which are used in Arduino, for example. These are 8-bit microcontrollers, and let's just look at what instructions do they support. So they support instruction add, it adds two registers. Add with carry, so A plus B plus carry. They have this add immediate to word, which is advanced instruction. Our microcontroller will not support it, but it's not really that important. So next is subtract. Okay, we can do subtraction. Subtract with carry also. Here they also have subtract immediate, but this is advanced instruction. We will not have it. And the next also. Next is logical AND. So our processor can also do AND, So next is AND with immediate. It's an advanced AND. We don't support it, but it's not a big loss. Or also, you can just OR two numbers. Exclusive OR, XOR, our arithmetic logic unit can also do it. One's complement. So one's complement is just inversion of all bits. How did we do it in our arithmetic logic unit? We calculate complement using NOT, which is just a NOT gate. In AVR microcontrollers, they do it a little bit differently. They subtract a number from 0xFF. And if you think about it, if then how to invert all bits, we can do it through NOT gate, or we can just set 1, 1, 1, 1, 1, 1, 1, 1, minus, for example, 1, 0, 1, 0, 1, 1, 0, 0. And so if the bit in our number is 1, then 1 minus 1 is 0. And if bit in our case is 0, then 1 minus 0 is 1. So also this is a second way how to calculate one's complement. So we could also implement it in this way. So here will be 0, here will be 1, 0, 0, 1, 1. Okay. So as you can see in microcontrollers, you can do the same thing in different ways. Next is how to calculate 2's complement. So one way that I mentioned was that you can invert all bits and add 1. So we go into arithmetic logic unit, and here it is. We invert all bits and add 1, and that's how we get 1's complement, 2's complement. However, in these AVR microcontrollers, it's done differently. It's done through subtraction. So first input is forced to 0, and then we just subtract the number using sub instruction. So it's 2 ways how we can do it. These set and clear register bits is, it's just OR with a constant number. To set bits, you take the destination register and OR it with another register. In this case, it's done with a constant. We don't support it, but we can select another register. And for clear bits, it's similar. So you're smart people, you're programmers, so you probably know it, but how can we set the bits? Let's say we have some input 1 0 1 0 1 1 0 0, and we don't know other bits, but for example, we want to set the bit number 1 high without modifying other bits. How can we do it? We create a mask with bit set to 1 in the location that we want to set in our original byte. And we just do OR. All bits will be ORed with zeros, so they will just be copied. But the one bit that we have in our mask will always be forced to 1 because 1 or anything will always be 1. So other bits are just copied, but this is set without modifying other bits and even without knowing what the value of other bits is. So this is how we can set the bits. And the next instruction is clear bits. So actually, we don't have separate set bits instruction because we can just do it with OR. And in these microcontrollers in AVR, it says that it has special set bits in register instruction, but in fact, this is a fake ghost alias instruction that is actually OR with immediate. Okay, so this is just shortcut for assembly language, but it's not actually a real instruction. It's just a different name to this OR with immediate instruction. Okay, so next is clear bits in register. How can we clear bits? We can create a negative mask and do AND, so let's say we want to set, okay, I'll change the input a little bit. So 0 0 1 1. Let's say we want to clear this bit here, the second bit. How can we do it? We have this mask 0 0 0 0 0 0 1 0, and what we first need to do is invert all bits, so we get 1 1 1 1 1 1 0 1, and then we do AND. So, and with all other bits, we'll just copy the bits because 1 and 1 is the same and 0 and 1 is 0. But here in this location, since we have a mask which has 0 and we are ending input with the mask, it will always clear bits. So clear bits in register, we don't have to have a separate instruction. We can just invert all bits of register B. So it's A and not B. So we can flip all bits of our second number and then do AND with our first number, and it will have the same effect. So we don't have to have a separate instruction for that. And so this AVR microcontroller also has increment and decrement. So it's just add one to a register and subtract one from register. So it's pretty simple. And our microcontroller also does it. And the next instruction is very interesting. It's called test. Let's say you did some arithmetic instruction and you need to check out what is the type of number that is stored in a certain register. So you can do either AND on register itself or OR on register itself. And what it does is it doesn't change the value of the register, but it updates the status flags in status register. So for example, if you do AND on number on itself, the number didn't change, but if it was 0, 0 flag will be set. If it was negative, if top bit is 1, the negative flag will be set. Signed overflow and this S bit, they don't change, so it doesn't matter. But these two flags, you can just update them to kind of touch the number without changing it. So again, in this AVR, this actually is a ghost fake alias instruction, and actually it is the same as AND the number with itself. So we can also do this. Then is clear register. How can we clear contents of register? We can just XOR it with itself, right? So, and that's how these processors actually do it. They don't have a special logic that loads 0 into a register. They just XOR register with itself. So let's say we have register 10100011, and we XOR it with itself. So XOR gives 0 if inputs are the same, and 1 if inputs are opposite. So 1 XOR 1 is 0, 0 XOR 0 is 0. So actually the result is just zeros. So clearing register is actually done by XORing the register with itself. Okay, next instruction is set register. And this one our microcontroller cannot really do, because there's no logic function that can set all bits of a register to 1. You can't really do it with AND or not like that. What you can do it in two operations. You can, for example, clear register, and then you can invert all bits of the register, calculating one's complement. So our microcontroller can do it, but it cannot do it in just, in one clock cycle. It will need 2 instructions, okay? And then there are these multiplication instructions. All microcontrollers that I know, all modern microcontrollers support multiplication. They have hardware multiplier built in using logic elements. It can only multiply integers like 5 times 3, I don't know, 100 times 2. It cannot multiply fractional numbers. It does not work on floating point numbers, but it works on simple numbers, integers, and it does it very quickly in just 2 clock cycles. But here's the catch. Multiplication, when you do multiplication, you need to be careful, because if you multiply 2 positive numbers, well, you get some result. If you multiply 2 signed numbers, you need to kind of be careful, because if both of them are positive, the result is positive. If their signs are opposite, the result should be negative. And if their signs are both negative, the result again will be positive. And the same goes for multiply signed with unsigned. So the first number is signed, the second is unsigned. Um, the results change a little bit. And this is why there are three separate instructions. And actually, there is, inside the microcontroller, there is just one multiply unsigned unit. But what it does is it takes two numbers. For example, if you do multiply signed, it checks the signs of both inputs. If they are the same, then it automatically sets that the result will be positive. And if they're opposite, then the result will be negative. Then it converts both numbers to positive and performs this multiplication on unsigned numbers. And if signs of the inputs were opposite, then it negates the result, it calculates 2's complement, and if not, then it doesn't. Because otherwise, microcontroller would have to have three separate multiplication units, one for unsigned numbers, one for signed, and the third for signed times unsigned number. But to save space, money, and transistors, it actually has unsigned multiplication unit, which just either inverts the result or doesn't invert result to 2's complement based on which instruction you're doing. So just fun fact, you know. And you don't really have to worry about it that much because compiler automatically selects the correct instruction based on how you have defined the inputs. If you define that it's unsigned integer, it will do multiplication on unsigned numbers. If you wrote simply int or signed int, then it selects the appropriate one. If you're writing the code in assembly, then you have to be careful with this. But, you know, that's all. So here's also something called fractional multiplication. I can't really tell you much about this. This basically shows you what happens here. This is like destination register times source register shifted by 1. I don't know what that means, whatever. But there are also these instructions. And also in this arithmetic logic unit, sometimes microcontrollers have also some kind of encryption hardware accelerator. For example, these AVR microcontrollers, they had data encryption standard block, which just quickly encrypts data. Modern microcontrollers often use AES, Advanced Encryption Standard, because DES was was announced as non-secure something like 10 years ago. So DES isn't really used anymore. But many modern microcontrollers also have advanced encryption standard calculator inside, and they do it really fast in hardware. So you don't have to write a very, very long code that does it. And then you make it wrong, and some results it encrypts faster, and some results it encrypts slower. And the hacker just sees, oh, it took slower, so that means that input was B instead of A, and all of your security is compromised. So microcontrollers have, for example, AES built in, which does it in a constant time. As a result, hacker cannot use a side channel attack to guess the passwords and so on. But our microcontroller, of course, doesn't support encryption. Okay, so that is about arithmetic operations, right? So basically, our microcontroller does like everything the other, except some special cases. And instruction directly controls general purpose register A, B, and operation signal, just straight away. So that's about arithmetic instructions. Next, there's a special case of arithmetic instructions, which is called compare. let's say you do something in your processor and you write some if then else statement. If A is greater than B, then do one thing, else do the other. So first thing is, how do you determine if A is greater than B? Actually, most of the time, it's just simple subtraction. You subtract A minus B, but unlike the regular subtraction, when you compare two numbers, you don't want the number to be overwritten. So if you did subtract A minus B, the problem would be that the destination result will be overwritten with the difference between these two numbers. Compare instruction performs subtraction, but in our general purpose register, it sets write enable to 0. So yes, the values are read. Arithmetic logic unit calculates the difference and sets data to be written, but instruction decoder checks out that it is comparison instruction. Instead of 0, 0, 0, 0, it starts with 0, 0, 0, 1. And this 1 just simply switches off write enable GPR signal. And as a result, the result is not overwritten. It is calculated. In the CPU, status register is updated, but result is not overwritten in GPR. So here we see how instruction decoder controls the processor. So if the first 4 bits are 0, 0, 0, 0, then it sets write enable high. But if, for example, we change in our microcontroller, okay, let's reset and change the instruction to 1, 5, 8, 7. Then instruction register sees, actually it will be 1, 5, 5, 7. Okay, whatever. It sees that first 4 bits are 1. So it sets write enable to 0. So this instruction will perform A minus B, but since write enable is 0, it will not actually write the result, but it will update the status register. What can we do? How can I show this to you? So register R5 is, for example, I don't know, let's say it's 4, and register number 7 is 5. So 4 minus 5 should be negative number. Let's check it out. MCU. This is 4, this is 5, result is -1. So when we do clock, the status register is updated on the falling edge of the clock, but the result isn't written into the general purpose register. And as we can see, status register new value is 5. What does it mean? 5 means that negativity flag is set and carry flag is set. And then, based on the value of a flag, we can, for example, jump to a different place in our code. This is why status register exists, and it's calculated, and this is why compare instruction exists. At the same time, we did the comparison, but the values of the inputs did not change, which is good. So that's compare instruction. And this, for example, this AVR microcontroller, it also has compare instruction. Compare, and as you can see, I wasn't lying to you, compare calculates one register minus the other, but it does not write the result anywhere, it just subtracts. And the second instruction is compare with carry. It is to compare two 16 or 32-bit numbers. You subtract parts of the numbers and also the carry from the previous subtraction, so you don't lose the bits. And we can do it. How can we do it? Actually, compare is we use it the same format as arithmetic logic unit, just the beginning of the instruction will be 0, 0, 0, 1, and operations are either subtract or subtract with carry. So they're going to be either 5 or 6 in this position. So you can see it here. Examples: compare R1 to R2. Beginning is 0, 0, 0, 1. Next is 0, 0, 0, 1, which is register 1. Register 2 is here, and subtract is 5, and subtract with carry is 6. So it's really compare and arithmetic logic unit instructions have the same control signals, except write enable is just set to 0. Okay? So, and advanced microcontrollers have, for example, compare with immediate. So you can compare register with not only another register, but with just some number that you give to the processor. But for the simplicity, our processor will not support this, but it wouldn't be really that complicated to add this thing. So next instruction that our processor should support would be, for example, LDI instruction. LDI instruction is instruction which just copies a number into the register. Load immediate. This is kind of strange language, but that comes from ancient times when the first processors were built. Copying something was called loading, and constants were called immediates. Okay, so this is just old language. Basically, it says copy value k into selected register, load immediate. Now, let's check out how can we modify our control signals to do this. So since in the first two instructions, the first 4 bits say what kind of instruction it is, and the next sets the destination register, then let's just use the same format for the first 8 bits also in LDI. So LDI code will be 0010, but the next 4 bits will be the destination register, just like in compare instruction and arithmetic logic unit instruction. So nothing really changes there. Instruction decoder for LDI instruction takes the second 4 bits from the instruction word and just forwards them to general purpose register input A and write input. As you remember, input A is the same as input for writing. And then the number, we have 8-bit microcontroller, so we have to be able to load 8-bit number. And since we have 16-bit long instructions and first 8 bits are used, then there's just no way around. Last 8 bits will be the number that we copy into our microcontroller. Okay, how can we copy value into register physically? As you can see, our general purpose register has address for writing select, which will be 4 bits, and it has input data to write. And originally, we only wrote the result of arithmetic logic unit into the general purpose register. Well, now what we do is we put a multiplexer in front, and using a special control signal, we just switch between arithmetic logic unit result and bottom 8 bits of the instruction. So instruction decoder has an output called low 8, which is the bottom 8 bits of instruction, and we just feed it right into this multiplexer. And if this GPR source signal is 0, then it feeds in the bottom 8 bits of an instruction into general purpose register. And if the bits are input 2, so it's 1, 0, then it copies arithmetic logic unit result into the general purpose register. So instruction decoder has a new control signal called GPR source, with which we can switch between what we want to write into the general purpose register. Okay, so, let's try it with an example. So for example, we want to load into register R4 number, I don't know, for example, I will write it in hex 0x78. Or maybe if it's hex number, I better write it with some hex letters also. For example, C5 or C4 if you have played Counter-Strike. So load into register R4 number 0xC4. So LDI instruction beginning is 000010. Next 4 bits is selection for destination register is 4, so it's 0, 1, 0, 0, I guess, is 4. And next 8 bits is the number, so C4 in binary. A 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0. Okay, something like this. And in hexadecimal format, that will be 0x, 0010 is 2, this one is 4, and this number is C4, basically. So if I go to my microcontroller, let's check it out. I'll write it in the second memory location. So I write 24 C4. I will reset and do it like this. So 24 C4 is already here. So when I do rising edge, this value is latched into the instruction register. And you can see it's 24C4. It has read and latched, copied, photographed this instruction. And what it does is top number 2 switches instruction decoder into such mode that this multiplexer selects and forwards the top 8 bits of the bottom 8 bits of this instruction into general purpose register input. So it says 196. So here is 196. This multiplexer selects this input and feeds into general purpose register. And address A is select as 4 because we want to write into register number 4. Of course, since the same bits are used for other instructions, like for example, arithmetic logic unit instruction, this C is also forwarded to arithmetic logic unit selector. But since this input will not be used, arithmetic logic unit can calculate, for example, register number 4 and register number 4, and C is some logical instruction, but this multiplexer will just not use the result. So you don't have to worry that the same bits are used for different locations in the processor, with these multiplexers, we switch between operations and between inputs and outputs, so nothing really bad happens. So instruction decoder sets multiplexer to input number 0, so it feeds bottom 8 bits into general purpose register write input. It selects register number 4 for writing. Write enable is set high, so when we do the falling edge of the clock, the value is latched into the general purpose register, and we can see that register R4 has our value C4, so it wrote it. And inside the instruction decoder, we can see this, that bottom 8 bits are used for address B, but they are also used for low 8, which goes to, for example, general purpose register, selector, multiplexer input. Okay, so yeah, they overlap, but it's not something bad. Okay, so, LDI instruction right here. With this, we can just set values to registers. Next instruction that we would need to look at is load from RAM, load from random access memory. Again, first 4 bits tell us that it will be load from RAM instruction. And basically the top 4 bits just increment by 1 every time we add a new instruction. Next 4 bits, again, select the register with which to work. So we want to write into some register. So we just use the same 4 bits to select the same register A, and the next 8 bits to select address. Okay, so for example, in this case, address would be maximum length will be 8 bits, so our random access memory is limited to 256 bytes. Bigger microcontrollers actually don't waste the bits so much and use extra bits from this LDR part, But since we want to build a very simple, very basic microcontroller, we'll just use these 8 bits to select address. And actually, for making it even simpler, we will only use bottom 8 bits for address select. So we only will have 16 bytes of RAM. We can have more, but for some reasons that we will look at later, for simplicity, we will just have 16 byte RAM. But how can instruction decoder manage this? Well, these 4 bits, it will again just forward to a general purpose register input A. And these bits, it will forward to random access memory address selector. So in our CPU, in our microcontroller, we have random access memory, which for simplicity has address selector. We select address with these bottom 8 bits of instruction, and it just forwards the data to the CPU. And inside this CPU, data in goes into this multiplexer, and instruction decoder selects that source for general purpose register data will not be bottom 8 bits, will not be input from arithmetic logic unit, but it will be whatever comes from random access memory. Okay? Right now it has question marks because random access memory enable control bit here, read RAM, is 0. But if we change this instruction to load from RAM, it will set it to 1, and actual data will come here and will be written to general purpose register, right? And for example, this microcontroller AVR, it has load instruction right here. It has a little bit different name. It's here called load direct from data space, but it basically says is copy value from random access memory. So we have this K, which is address, and it just looks up what is written in random access memory address K and copies this thing to destination register. Okay. Now you are programmers and you will understand this really well. Um, all microcontrollers also support load indirect instruction. If you know what is a pointer, you'll like immediately get it. So basically our microcontroller, we will not build it, for simplicity, but microcontrollers have this thing that you can copy a value from random access memory, which is not pointed by a constant, but which is pointed by another register. So for example, register R5 contains value 66, and you can do this load into register R0 value from address which is pointed by register R5. So for example, R5 has number 66. So it will copy into R0 value that is stored in memory location number 66. So this is called load indirect. So one of the registers is pointer, and you can load the value of the memory location which is pointed by another register. So in C programming language, how would it look like? Sorry, this is the wrong file. So for example, load indirect would be, for example, LD R0 R5. In C programming language, it would be R0 equal to value pointed by R5. And R5 contains an address, and you just dereference it. And here's a really cool thing. Microcontrollers, since putting an adder inside the CPU isn't really costly, actually you have arithmetic logic unit, you can use it for that, or you can just put a small adder and subtractor, and microcontrollers support load indirect and post increment, and load indirect and pre-decrement. So basically, it loads into register value that is pointed by another register and increment the pointer by one in the same time. So its value is sent to the RAM address. RAM contents pointed in that address are copied to destination register, but the source is incremented by one automatically. So basically, microcontrollers in single instruction can also do this. R0 equals to value pointed by R5 and R5 incremented by 1. Now, these are 8-bit microcontrollers. So this value is always incremented by 1. So if this would be a 16-bit number pointer, you would still need to add another 1 to R5 because, but at the same time, register R0 is 8 bits. So if you were working with 16-bit numbers, the result would also occupy 2 registers. So you would do this 2 times, it would automatically increment. And this load indirect and pre-decrement, how would we write that? R0 equals to value pointed by minus minus R5, something like that. So pre-decrement R5, I think that this pre-decrement is higher in hierarchy than the reference operator. So I guess this would be done first and then the reference here. So C operator precedenza, blah, blah, blah. And in our post increment and decrement, prefix increment and decrement, and then indirect, and it's right to left. So right is done first, and then left. Reduce R5 by 1, and then load value pointed by R5 minus 1 into register R0. I guess this is how it would work. So microcontrollers have this thing like hardware accelerated. In this way, working with arrays in microcontrollers happens very naturally and very quickly. So you can copy large amounts of data, and it basically does it in something like 2 instructions instead of 4 or 5. Okay. Next block of the instructions is, we could read from RAM, and we have to be able to store into RAM. And the reason is because microcontrollers have too few registers. Not all variables fit in the registers. So obviously your variables in your C program, they will be stored in random access memory. So our microcontroller will also support store instructions. And so, top 4 bits is that it's a store function. Next will again be used as address A selector. And the last 8 bits will be used to select in which random access memory address to store the value. And to do that on the microcontroller, instruction decoder just simply forward select A here, and address out should be used. Address is right here, and data out will be taken from register A. So we select register A, its contents are forwarded into data out, it's sent to random access memory, and address, in our case 4 bits, but up to 8 bits, will be forwarded as address pointer, and the value will be just written. And random access memory has this write enable signal, and in that case, write enable will be set high, so it will be stored. If you want to, we can do a simple example. Let's say we want to store register number R6 value into memory location, I don't know, in memory location 0x03, for example, there. So store is 0100. In this case, it's like a source register, but it's still register A. Value 6 is 0110, and address 3 is 00000011. So, and in hexadecimal numbers, this is 4, 0x4, 6, 0, and 3. So writing this number into our CPU microcontroller. Okay, I can maybe write it here. 4603, and then I will write some value in the register R6. So you believe me, I'll write, for example, 42. When I do clock rising edge, this instruction is latched into instruction register 4603. It's right there. Then instruction decoder sees, okay, top bit is 4, so I need to set write to RAM high. As you can see, it did it. Then it also needs to select register number 6. As you can see, it selected register number 6. It just forwarded the 6 here. So values of the register 6 should be 42. I don't know. Oh, it's in hexadecimal numbers. Okay. So its content 66, decimal is 66, is output right here. And this multiplexer instruction decoder selects it to position 0. So this 66 is set also as data out, which goes to random access memory. And this 03 is forwarded to address. As you can see, it says 3. So address number 3 is selected. And this multiplexer selects 0 input, so it's the same. And when I do the falling edge, here you can see that in RAM address number 0123, number 42 is stored, okay? And store to RAM, you know, okay, we will not talk about jump and branch instructions today, but let's just look at how can we build this instruction decoder. Actually, it's not that difficult. Bottom bits are just forwarded to registers and to some switches, and there are some control bits. But what we do is we just make a table where we write all the control bits, for example, GPR source 1 and 0, write to RAM true or false, read from RAM true or false, and some others, which we'll look at next time. And then we go through each instruction and we just write in, should it be high or low? And we create this table, and then we just slowly implement this table right here through lookup table. So for example, instruction 0 is arithmetic logic unit instruction. So it sets update GPR to high, and I don't know, force PC +1 to high, and other instruction types change these accordingly. So, you know, it's not like very complicated. So this is how microcontroller works. And on this note, I will end the lesson today. Next time, for example, we can look at the jump instructions and branch instructions. How do we change the course of the program depending on some conditionals? Okay, so if you have some questions, you can ask